Well, the second presentation in this AVC Player playlist offers you some hints to start your work concerning stage 1 of this learning assignment. After watching this presentation, you shall be able to list what are the main blocks needed to implement this stage, and also to explain the operation of the control path ASMD chart. Now you may recall that on stage 1 we simply want to play a tune on the PC keyboard. That is to say, as we go on pressing the keys that were allocated to octaves 4 and 5, the corresponding frequencies shall be sent to the loudspeaker. These musical notes will then be generated using a square wave as represented in this slide, which is generated by a toggle flip-flop with enable. Actually, the enable input for this flip-flop is generated by the ticking pulse at the output of a modulus M counter, and the modulus M counter is used to define the period of time corresponding to the frequency of each musical note. That is to say, for each musical note that we wish to play, a corresponding modulus counter limit will be set to its inputs, and the counter will count up until it reaches this limit and will then restart its operation, and at the same time generate a ticking pulse at the output that will be used to enable the toggle operation at the output flip-flop. So this means that for each musical note a new m_in limit will be imposed to the modulus counter, and so the lower the frequency that we want to generate, the higher limit for the modulus counter, that is to say, the higher time period for the output waveform. Now the toggle flip-flop with enable, the operation of this block is simply that whenever the enable input, which in this case corresponds to the t_in signal, is at 1, then at the next rising edge of the system clock the output will toggle. And this means that we will have 2 ticking pulses for each output waveform period, and this will have to be taken into account when we calculate the limits for the modulus counter corresponding to each frequency. You shall notice as well that the toggle flip-flop has a clear flip-flop signal that will be able to override the enable input. That is to say, if the clear flip-flop signal is active, then this will flatten the output waveform. That is to say, it will mute the loudspeaker. Now, apart from the output stage, we will also need a code converter and the UART receiver itself. The UART receiver is responsible for deserializing the information coming from the receive data line, coming from the PC, and by producing the corresponding ASCII code in 8 bits for each key that is pressed in the keyboard. Now, this ASCII code, each ASCII code will correspond to a different limit for the modulus counter. So a code converter is required to generate the appropriate modulus counter limits for each musical note to be played. Now, the number of bits at the output of the code converter will be necessarily different from the number of bits at its input, since the modulus counter limit for each musical note will depend on such factors as the frequency of the clock signal. Actually, the way to calculate the content of this code converter block simply consists of counting how many system clock pulses are required to generate the necessary time period for each output frequency. If we take the worst case, which corresponds to the lowest musical note frequency, then we know what will be the duration of this interval corresponding to half a period. And if we assume that the system clock runs at 100 megahertz, then we will simply have to determine how many system clock pulses will fit into this half a period of the output waveform. And the number of clock pulses that fit into this time interval will dictate the modulus counter limit for that specific musical note. Now, if we calculate that for the 7 musical notes in octave 4 and the 7 musical notes in octave 5, we will be able to define the table that underlies the design of this code converter. Altogether, the elements that are represented in this slide represent the data path of our complete FSMD for this stage of the ABC player. So what is missing here is simply the corresponding control path that is made up of a finite state machine, as you know. Now, this representation is now equivalent to the full set of elements that are required to implement stage 1. The control path finite state machine will be required to generate the clear flip-flop signal going to the data path output driving the loudspeaker, and it will do so based on information concerning the arrival of a new ASCII code from the UART receiver, and also on the value of the ASCII code that has just been received. Now, the value itself is necessary because we may receive ASCII codes that do not correspond to a valid ABC note, and in that case the clear flip-flop signal shall be set to 1. So actually, if we look into the ASMV chart, as we will do in a moment, the inputs to the control path are those signals that will be used in the decision boxes of the ASMD blocks, and the outputs coming from the control path into the data path are the signals that will be represented in the square boxes in the ASMD chart. Now, the square boxes comprise the state box, which is represented with square corners at the beginning of each state, and also eventually conditional output boxes, which are represented by rounded corner rectangle boxes. In this case, we will probably just have state boxes because we have only one output, which will be a Moore output. Now, it is important, before progressing, that it is important to call your attention that the ASMD chart that we have to draw corresponds to this control path. The ASMD chart that we want to draw, I repeat, corresponds to the operation of the control path. The data path, as you see in this slide, comprises, as we already know, regular sequential circuits like the modulus M counter and the toggle flip-flop as well. Also combinational blocks like the code converter, and even eventually other smaller FSMD blocks like the UART receiver itself. All these blocks are part of the data path, and we assume that they will have been designed before and be available in a library, or that we may have to design each one by its own. But the final step, which consists of drawing the ASMD chart for the control path, will define the behavior of the Walsh circuit. Now, I would also like to call your attention to the fact that I've represented in red those signals that I consider to be at the top level of our design. Actually, our design will comprise a number of VHDL files that will be created in the Xilinx design tools. We will have one VHDL description file for each of these blocks, and the corresponding inputs and outputs have the names indicated here, and they will be used in the entity declaration for each of these blocks. Finally, when all the individual blocks have been represented in their VHDL description files, we will create a top-level description in VHDL, which will use the top-level signal names that are represented in red in this slide. So the block diagram that you see here is quite important, and we will come to use it various times during the actual design phase. Now the ASMD chart itself is quite simple, and in this case we simply need to alternate between two states called mute and play. And the only difference between these two states is that in mute we set the clear flip-flop output that you see here going into the output stage. We set it to 1, meaning that the output waveform will be flattened. It will always be at 0 while we are in the mute state. Now, while we are in mute, we will ask, did we receive a new ASCII code from the UART? That is to say, we are asking if this RX_DONE_tick signal is active. So this decision box corresponds to this information input to the control path. If this is true, then we will ask, is this a valid code belonging to octave 4 or octave 5? And this is being done based on the information that comes from the data out bus, that is to say the output, the parallel output from the UART. If this is true, if the new code that has been pressed corresponds to a valid ABC note, then we will go into the play state. And the play state will set the clear flip-flop output to 0, meaning that the output stage is now able to generate the square wave containing a frequency that corresponds to the current ASCII code that has just been received. So this code is now available at the inputs of the code converter, which generates the counting limit for the modulus counter corresponding to the current ASCII code that has just been received. Now, while we are in the play state, we will continue to ask, has there been a new code received? If not, we continue to wait, and the musical note that has just been received continues to play until a new key is pressed. Now, when a new key is pressed, we ask if it is again a valid ABC note. If that is true, then we will continue in the play state, and the new code will dictate a new limit to the modulus counter, that is to say, a new frequency to the output waveform. Otherwise, if the key that has just been pressed is not a valid ABC note, then we go back into the mute state, we flatten the output waveform, and we now wait for the next key to be pressed. Well, in this slide I simply show you what could be a template for the architecture body of the FSMD control path description file. That is to say, we are referring to the VHDL description file of this FSM that you see in the block diagram. This simply comprises the standard state register and next state and output logic sections, and you should feel comfortable in filling in the information that is shown here. Please follow this template because it makes it so much easier to check if there are errors when we simulate and find unexpected results. Now, the results of simulation concerning the implementation that I have prepared for this presentation are shown in this slide, and I am assuming that well, my test bench has imposed the reception of 3 keys, one corresponding to the lowest frequency musical note in octave 4, the second one corresponding to the highest frequency musical note in octave 5, and finally the third key corresponds to space, which should be used to mute the loudspeaker. So indicated in this diagram are the intervals when each of these 3 ASCII codes are being received. So in this case we are receiving the ASCII code corresponding to lowercase r, and this will be the first key for octave 4, so it will correspond to the lowest frequency musical note, and the corresponding output waveform is seen here. Now, during this period, you can see that the output of the code converter shows the ASCII code for lowercase r, and the output of the code converter contains the limit for the modulus n counter corresponding to this musical note. Now, when we go, well, you see that we are in the play state all throughout this period, and we were previously in the mute state before the first ASCII code had been received. Now, when the second ASCII code is received, because it corresponds to the highest frequency note in octave 4, it is still a valid code, and so we continue to be in the play state. And the new limit for the modulus counter is generated by the code converter, as you see here. Finally, when the space key is pressed, then we will go from play into mute, and correspondingly the clear flip-flop signal will be asserted. That is to say, it goes from 0 to 1, meaning that the output waveform is now flattened and the loudspeaker is muted. And of course, you see that the output from the UART is now 2-0, which is the ASCII code for space, and the code converter is now sending the standard pattern that corresponds to a non-valid key. Now, you may notice here that when we change it from the lowest frequency waveform to the highest frequency waveform, the output stayed at 1 for an unexpected long time, instead of just starting immediately with the new waveform. And I had included this question to call your attention to this fact. It actually happens that the template that is recommended in Ponchou's book for the modulus n counter, which is corresponds to listing 4.11, if I am not wrong. This template considers that the counter shall output the tick signal and restart its operation when the output is equal to the limit set for its modulus operation. Now, what happens in this case is that we went from the highest possible limit corresponding to the lowest frequency waveform to the lowest possible limit corresponding to the highest frequency waveform. And at the moment that the new limit was sent to the modulus n counter, its outputs had already counted past that value. So it is not equal to the new limit. It was actually greater than the new limit when it was sent to the modulus counter. And so what will happen is that the modulus counter will just count up to the maximum value at its outputs, will overflow, will restart at 0, and then it will be able to reach the new limit. So I leave it up to you how to change the code in the listing offered in the book in such a way as to avoid this unexpected long time when you go from the lowest frequency waveform to the highest frequency. I will also show you some detailed waveforms corresponding to the moment when you go from one ASCII code to another. So you see here that we are going from code 7.2 to code 6A, and this corresponds to the moment when we receive the ASCII code for the highest frequency note, so to this period indicated here. Now you will see, if you zoom into this period using the zoom functionality of the iSim tool, you will see that as the deserializer comprised in the UART receiver operates, there will be an intermediate number of patterns that will be output from the UART, and this intermediate number of patterns, while you go from 7.2 to the new code, which is 6A, they will actually be sent to the code converter, meaning that in this case none of them corresponds to a valid ABC note, so the code converter will output the standard pattern for this situation. But the question is, if it happened that any of these intermediate codes at the output of the UART might correspond to a valid ABC note, then the code converter would output a new pattern, a new limit to the modulus counter, which wouldn't really have any meaning because it was just an intermediate pattern showing at the UART outputs. Now, it will probably have no importance from the real point of view. I mean, you won't notice any difference in the output waveform, but you could change the output stage of the UART receiver, which is described on page 170 of Peng Shu's book, in order to make sure that these intermediate patterns were not visible to the code converter, and I leave it up to you to complete that task. Finally, I have a few questions to ask you. One of them is, how would you qualify this design in terms of energy efficiency? And in order to think about this aspect, I recommend you to look at the modulus M counter in the data path. Can you suggest any modifications in the operation of this modulus counter that could improve power saving? Second question addresses the possibility of generating alternative waveforms at the output. So if we want to generate a sawtooth or a triangular wave, how should we modify the output stage? I mean, it will probably be necessary to use a DA converter instead of just a simple toggle flip-flop, but how should you do it in order to enable a sawtooth and triangular waves? And finally, if you wanted each musical note to play for just half a second, instead of just playing until you press a new key, what would be the required modifications to the block diagram that has been shown earlier?